Okay, so welcome everyone to this special colloquium. So it's a great pleasure to have Professor Hugo Touchette, who will give this lecture. So Hugo is a professor in the Department of Mathematical Sciences in Stellenbosch University in South Africa. He's an expert in the areas of non-equilibrium statistical physics, Markov processes, and large deviations in particular. He has written one of the most popular and easy to read reviews on large deviation theory, which is the starting point for lots of physicists in this area. And has made a lot of very interesting contributions in large deviation theory, particularly for dynamical systems. Hugo is, I think, very well known as he's a very popular lecturer. Like recently I organized a school in Lejus, and he was like, when I asked the students, like he was the most popular lecturer in the school. And he's actually giving a set of lectures from next week on machine learning at ICTS. Hugo is a regular visitor to ICTS. He has been coming here for a long time. So it's a real pleasure to have him here back again. And we're really happy that he agreed to give this special colloquium on the Nobel Prize this year. So I also want to thank Spenta, who I think kind of convinced us, Hugo.
Thank you, Abhishek. Thank you for the introduction. I'm here for 2 months, so if you want to discuss after, then there's plenty of time. I'm here until the end of November, visiting Abhishek and then spending the last part of my sabbatical here. I should start by saying that I'm only partly qualified actually to give this talk. I'm a physicist. I do teach machine learning, so I'll be giving the reinforcement learning course in November here for 4 weeks, but I don't do research in machine learning as such. I use a lot of machine learning tools, but I think I know enough, and the situation was that Spencer actually saw me, and then he kindly asked if I could actually explain the machine learning contributions to the Nobel Prize, and of course, I couldn't say no. So here we are. Thanks for coming, and so many of you. So as you know, the 2024 Physics Nobel Prize was awarded to John Hopfield and Geoffrey Hinton for foundational discoveries and inventions that enable machine learning with artificial neural networks. John Hopfield is working at Princeton University. Geoffrey Hinton actually is from England, worked in the US, but spent most of his career at the University in Toronto. So the goal of the presentation is to try to explain what these contributions are. I think, as you know, the Nobel citations are always quite general and don't say much. So we'll try to understand what this means. And then I'm not going to discuss so much the context or the controversy, if there's any, or the philosophical consequences of giving a Physics Nobel Prize to a computer scientist. So this is something we can discuss after, at the end maybe. But we'll see actually that the contribution of Geoffrey Hinton, who's a computer scientist, is very much related to physics and is in fact deeply rooted in physics. And so that's the goal. Now, before I go into describing the contribution, maybe it's a good idea to discuss what is machine learning and what is learning. So learning is really, it's a general method, or it's the basis of pretty much anything in this world. And it's essentially learning a model or representation of something. Even when you learn a language or you learn to walk, you're actually building a representation for a task or for a goal. So the general template that we have is that we have the world around us, and we have some observation or data coming from this world. And what we want to do is to build a model or representation of that world. And in many cases, that representation will be a function. You have some input observed, and you want to predict what the output will be in terms of causal dynamics or in terms of prediction of something. So what we want to learn really, what learning is about, is learning a function. Y is f of x, and x is the input, and you want to learn the mapping of the input to the output. And so what we're doing is that we're just build a model, so we build an approximation of the true world function that will involve some parameters that I call theta, and then we want to learn the right set of parameters that will approach the true function the closest. So this is learning. This is learning at the level of a deterministic system. And as you know, there's uncertainty and randomness in this world. So really learning can be pictured in a more general way as learning a distribution. So you want to learn a random variable. And so you want to approximate what the true distribution of the world is for a certain particular set of observation by some approximation of that distribution involving also parameters. And you want to fit those parameters in order to learn what the true distribution is. And I'll come back to this. This is really important. The way we teach machine learning, actually in a modern way, is that we tell the students that learning is about learning distributions. It's not so much about learning mappings. So in this sense, learning is really just a fancy word for fitting. As you learn, you fit something, you fit a function, you fit a model, you fit a bunch of parameters or a distribution to a given set of observation, and this will be important. Now, machine learning in that context is just learning done by a machine. But machine learning as such is a huge topic, just like physics is. So if I was here to say, oh, let me explain to you what physics is, I would be here for many years. And so we could do the same for machine learning. And this is this huge area involving, in fact, different subjects like physiology, psychology, neurology. I'm just mentioning some of them. And on our side as scientists, it's heavily based on mathematics, statistics, and computer science. But there's also lots of physics into this, and then this is what we'll be discussing. And the part that I'll be discussing mostly, which is really the subject of the contribution of the Nobel Prize, is this supervised learning part using neural network, which is what drives most of the technological applications that we see these days, like ChatGPT or image classification. All of these engines actually are based on artificial neural networks, and there are many architectures. We'll see some today, but you have many architectures of neural network that have been deployed over the years to achieve some task. And then the latest that is really the one in fashion is the notion of transformers, which is the architecture used by ChatGPT and the modern engines like ChatGPT. So what we'll be discussing today actually is the first one, Hopfield neural network. And the contribution of Hinton is on this area of Boltzmann machine and restricted Boltzmann machine. So this is the template, more or less, of the neural networks that we use these days. You have many layers. I'll come back to this. And then you have some kind of neuron. You have nodes, which are neurons. And then you have connections between the nodes, which we'll call weights. And this is done in the kind of stack layer. There's a direction to this, so we call this the feed-forward neural network. And then I'll explain eventually how we go from the input layer through the hidden layers to the output layer in order to represent a function. In a sense, a neural network is a very efficient representation of a function, so it's a very efficient way of approaching this f of theta, or the true f that you're trying to represent as an input-output relationship. Now, neural networks have been around for many, many years. So why are we hearing so much about them now? There are many reasons for this, and one is computational power. Neural network, we'll see in the next slide, were actually invented in the 50s. And so we're here now actually deploying neural network because now we have the computational power to do so. Before, many of the computations that we do now routinely actually couldn't be done with computers because they weren't good enough. So we have the computational power, and then we have also the availability of data. There's lots of data now, and then we can use that data to train neural network, and so to do the training needed to achieve learning. And then on the computational side, we also have a number of packages actually that make all of this, the coding of neural network, very efficient and very easy. So if you've tried yourself, you probably know these packages. PyTorch and TensorFlow. TensorFlow is from Google, PyTorch is from Facebook, Meta, and these are very efficient implementation of neural networks and different machine learning tools that are useful for us because they spare us from coding hundreds and hundreds of pages or reinventing the wheel at all time. Okay, and these are packages in Python. So this explains why we're dealing with this now and why this is so important. In a sense, the ideas are old, but the applications are new because we have the ability to implement this idea. And this is driving research, of course. There's lots of new things appearing all the time because of these applications. So let's go a bit into the history of this. So I've mentioned 1950s, but actually it goes a bit before this. The major work that actually established the neuron as a computing unit is this paper by McCulloch and Pitts, which actually, as physiologists and engineers, looked at the neuron in the brain and think, okay, how is computing achieved in the brain? So we have different neurons, we have kind of input signals, a kind of processing part in the the cells of the brain, and then we have some outputs, and then these neurons are connected in some funny way, and so they propagate signals and process signals. So they wanted to come up with the mathematical abstraction of these neurons, and the one that they come up with is what we call the perceptron. So the perceptron is a very mathematical, is an easy mathematical construct where you have a bunch of signals as inputs, you weight them in a certain way, you sum this, so you have a weighted sum of the inputs. You can put some bias there, actually, so you can put some constants in the processing if you want, and then you take the sign of this, and this determines now the output of the neuron, of the neuron itself. So, of course, it's probably physically not what's happening exactly in a neuron, but this is the abstract mathematical model that they've come up with in order to model this. And this now is really the building block of everything that we do with neural networks. So transformers, feed-forward neural networks, they're all based on this, and I'll explain this. What changes is the sign function, what we call the transfer function, for actually giving the output as a weight in sum of the input. And it's very important that you take a nonlinear function, and I'll come back to this. So this is the first step. And then from there, you had many studies in psychology and physiology about how, okay, so you have the neural dynamics, but how do you actually learn? And then there's a book of Hebb actually on this, on learning principles. And the idea is that stuff that have a positive correlation actually should participate into the learning. And so they should reinforce in some way. So this is an intuitive idea. This is called Hebbian learning. And then there's another step coming after, which is the work by Rosenblatt in the 50s on actually building perceptrons physically and trying to stack them and connect them in order to achieve some kind of learning or representing some function. So at that point in McCulloch-Pitts, actually, it's a mathematical study, and then the first experimental study of this came with the work of Rosenblatt. So there's lots of things here. I'm not going to do the whole history of the field. I'm actually not qualified to do this, but there's a big period where not much is happening, and the work of Hopfield is coming in 1982. So you see there's a big gap, which actually is called what we call the AI winter. Oops. AI winter, and I'll come back to this actually to explain why we have this period there. And the contribution of Hinton is 1983. So I'll discuss these two. The main idea of Hopfield is that you can connect actually these perceptrons together and achieve some kind of learning as a kind of dynamics. So you can actually define a dynamics with all these connected networks, and then you can achieve learning into this. And then later on, actually, Hinton came with the idea of having hidden units, so hidden perceptrons in the neural network in order to have a more efficient learning. And this is the basis of the Boltzmann machines, which in a sense are kind of the first versions of the deep learning neural networks that we have right now.
Just a quick question about the Hebbian learning that you were talking about. So I think usually when people in neuroscience talk about this, they say this pithy thing about neurons that fire together, wire together.
Yeah.
So maybe can you say something more in the context of this perceptron picture, what that would imply? Does it mean that the weights that go into all of this are correlated? Or
yes, yes. We'll see this actually in the Hopfield dynamics, and we'll see this also in the Boltzmann machine, actually. And so Hebbian learning is really into the thing is that if you read Hebb, actually, you don't see much mathematics. It's really this psychological idea that, as you say, neurons that are firing together should be correlated. And so learning is done like this. You want to correlate things that fire together in order to enable learning. But the mathematical consequence of this, or the mathematical representation or expression of this, we'll see actually is very clear in the Hopfield network. Okay. Please stop me anytime if you have any questions. This is like has to be seen as a presentation, but discussion also of what it means for us as physicists to have this Nobel Prize. Yes. We'll see this. Essentially, if you have two layers, it's deep. Okay. Okay, so let me start with the contribution of John Hopfield. His contributions from 82 actually relate to two important papers published in PNAS, so 82 and 84. These are the titles, and these papers kind of introduce Hopfield, the notion of Hopfield networks. Actually, these networks come from work coming before in 72 by Amari, a Japanese computer scientist, on recurrent neural networks. And this is very clear in computer science. In a sense, I mean, but this is slightly controversial, but Hopfield did not invent Hopfield networks. Okay, but I'll explain what the contribution is, though. It's really important. So the idea is to use the perceptron in a connected way, in an associative way, and then we'll see what associative means in this case, to build associative memory that can learn or store some patterns. Okay, so you can learn some patterns and retrieve those patterns in some ways. So the real contribution, if you read the paper, is that there's a deep connection with physics, which is really explicit in the paper. So Hopfield, I would say the real contribution is to make the connection with statistical physics, especially with spin glasses and optimization, and that opened a massive door actually in people doing research in computer science. In fact, it opened the door to a whole bunch of physicists who started working on neural network from these papers. So this is a massive contribution from that point of view, and I believe this is why the prize was given. For his contribution, Hopfield was awarded the Boltzmann Medal in 22, actually with Deepak. Deepak is here. Yes. Okay, so what is the Hopfield network? So a Hopfield network is a connection of perceptron. It seems I need to be very close. So you have a bunch of states, which you can take to be 0 or 1, or here I'll take them to be minus and +1. So you have these states there, they're connected. You have different weights linking those states. So the weights will be weights ij. They actually be symmetrical. So it's represented as an undirected graph. And then you also have a bunch of biases. And the idea is to define a dynamics for the weights. So you have a weight at a given time, and then you want to find the state at a given time, and you want to find the new state of a neuron at the next time. And the update is really the update of the perceptron. So you take the weighted average for a given node actually coming from all the neighboring nodes, actually from all the nodes, everything is connected here. So you have weights like this. You can apply a bias, this is not necessary. And then you take the sign function in order to propagate now for the new state. You can do this in a synchronous way, or you can do this in an asynchronous way. It doesn't really matter. And so you have this dynamics. And the point of the dynamics is that for a given choice of weights, you want to actually reach a certain configuration of states, a certain pattern of states that will be recognized as a pattern that you want to store. Okay, so the idea is, for instance, suppose you want to store 0 as an image. So you have to imagine that each of the cell is actually a state. Each of these states are connected with weights. And then initially, you're going to have some initial condition for your network. So the network is really the configurations of pixels there that are all connected. This is your initial state. And then you need to find the weights in order for the dynamics to reach the true 0 that you want to store. Okay, so the true 0 is the target state. And what Hopfield has shown is that if you choose the weights this way, then the dynamics actually will converge to your target state. Okay, and this is quite nice. In fact, they will converge to the target state if you don't have more than half of the bits being away from the target state that you have. Okay, and so from a large pool of initial conditions, if you propagate the Hopfield dynamics with those weights, you will reach the pattern. And this is Hebbian learning. You see, the weights, the states are actually enforcing each other because you multiply the states that you want to reach. Okay, so this is one contribution. Now, this will store only one pattern, but you can generalize this to multiple patterns. So if you have multiple patterns, say you have P of them, then you can do the same. And in this case, you can also find the weights for this, and then you can store many patterns. I'm not going to explain what this is, but in a sense, then you have a certain pattern, and then the dynamics will go to the pattern. The other contribution of Hopfield was to show that this is actually an energy minimization dynamics. So the Hopfield dynamics is somehow minimizing some energy. It's going into an energy minimum. So there's a Lyapunov function for the dynamics. And so the pattern that's reached will be the ground state of some Hamiltonian, which will be quite complex. And then it's this kind of Hamiltonian. And then for us, this is natural. This is the Hamiltonian of a spin system with different weights for all the connections. So it looks like a spin glass. So you would have to fix the different weights according to the pattern that you want to reach, to store. And then you will define like this a given spin glass model. And so the Hopfield dynamics is just the dynamics and that energy landscape reaching different minima of the energy, the Hamiltonian. And each of these actually will be storing different patterns. So this is a picture you can see actually on the website of the Nobel Foundation for this year's prize. And so this is an illustration in picture of what the Hopfield dynamics is doing. And this is really important. This is a really important contribution because it changes how we perceive learning. And now we perceive it in a very physical way as minimizing some energy function. And that brings, as I said, then the whole field of physics into the picture and a whole bunch of people working on spin glasses. So for the Hopfield Hamiltonian, actually, this is, I'm not going to derive this in any way. This is the Hamiltonian that results if you want to store P patterns. So these are the target states for the patterns, and these are the weights that you're gonna choose. So this looks again like a spin Hamiltonian, just in a very complicated way. Again, the connection with spin glasses and the learned patterns being ground states. And here also we have this notion of an inverse physics problem. We have some patterns that we want to store, and so we have to fix the physics, the weights, in order to reach those patterns in the dynamics. So see, there's an inverse problem. In physics, you would write down the Hamiltonian and it'll try to solve it in order to get the ground states. Now we just go from bottom to up. Now, so this can be used, you can actually code this on a computer if you want. This is quite interesting. The problem is that there's not that many patterns that you can store in a given Hopfield network of a given size. And then moreover, if you want to learn a pattern, if you want to recognize a pattern, you have to actually run the whole dynamics in order to reach the pattern state. And so this is quite slow as an engine actually to recognize pattern. Okay, it's not so efficient, but it's the first step towards building a more efficient one. There's also a limited number of functions that you can store, a limited number of patterns that you can store. There's some theoretical estimates for this, and basically the fraction with a given size. So if you have a neural network of size n, then you can store more or less like 15% of that size in terms of pattern.
If you start with random initial condition, then with some energy minimizing dynamics, it will go to one of the P.
Yes. So the thing is that the initial condition, though, has a basin of attraction. So, right, you have an initial pattern which is close to what will be recognized. So in a sense, it recognizes noisy pattern, or it makes error correction. So you have an initial pattern which is not quite the one you want to recognize, and it cannot be too much away from the pattern that it can recognize. And the bound is n/2. So the number of pixels that are wrong cannot be greater than 2 in order for the pattern to be recognized. That defines the basin of attraction. So each of these energy minima have a basin of attraction defining the recognized pattern or the pattern to be recognized. Okay, this is really important.
Are all ground states the learned states, or?
Not necessarily. The Hamiltonian, I'm not sure, actually, I'm not expert enough here, but there might be more minima of this energy function. But for sure, you're gonna store the P of them. I don't know beyond that. I haven't made any research on this myself, but it's a very easy dynamics to code. So I would actually encourage you to do this, and then you can try it out yourself actually to see from a given initial condition where what you reach in terms of recognized states. Yes, there's a question.
These xi is a vector, right, over however many points you have on that grid. So this is like taking the dot product of two vectors, squaring it and adding it up. So it somewhat looks like a loss function.
Yes, yes.
Like it's some vector that wants to align with this vector, and there the energy would be minimum.
Yes.
So by using Cauchy-Schwarz or something, shouldn't it be possible to show that those P states are the only minima?
It might be the way, yes. That's a good idea. So the two papers of Hopfield actually were into showing that it's an energy minimization dynamics and proving convergence, and then having that bound of n/2 in order to prove convergence, and then showing how you can store them more than one pattern.
Yeah, but I mean, loss functions also work like this, right? You take some difference and then you square it.
Yes.
Here you're just taking the dot product and squaring it and adding it over your P things.
Yeah.
Okay.
I'll come back to this. So the notion of loss is really important. So the idea that learning is about minimization is really the modern idea of learning. And then it will come again and again later on. Now, the starting point of Hinton is this problem, the fact that you have low capacity and then a slow dynamics to do learning. So you're learning a kind of function, you're learning to recognize patterns, but this is not an efficient machine actually to do learning. So starting from there was some work, and then the contribution of Hinton is really along making this more optimal or more efficient. So before I go there, so just a few bits of information. So Geoffrey Hinton, I said, was born in England, worked in the US, but then moved to Canada as a more stable place to do research. So spent quite a lot of his career there. Turing Award in 2018, actually, for deep learning with Yosha Bengio, who's in Montreal, and Yann LeCun. He worked at Google. He's quite famous, actually, for quitting Google in 2023 because he had some qualms about the research that was done there. And he's known as the godfather of AI. I'm not sure what this means, actually, because he's not the father of AI. So what is being godfather of AI? I'm not so sure. He didn't commit any crime, actually, in the name of AI, that's for sure. We can discuss this. There's one funny quote I got, actually, from the New York Times interview for the Nobel Prize, is that Hinton failed at physics, dropped out of psychology, and then joined a field with no standards at all, artificial intelligence. So apparently this, I couldn't trace the quote, but this is apparently somebody who introduced Hinton for some talk. So that's the background of someone winning a Nobel Prize. Right, so his contributions are this invention of Boltzmann machines, especially restricted Boltzmann machines. So this is what I'll be discussing. He's also famous for introducing autoencoders, which led to the invention of what we call variational autoencoders. And the big idea behind these contributions is the notion of hidden units and the notion of learning as gradient descent. So I'll mention the idea of backpropagation. If you've worked with neural network, you know that backpropagation is really crucial for the learning. He's not the inventor of backpropagation, but for sure, he's the one who popularized the idea of backpropagation. So I think I'll discuss this. Now, the fact that this is all related to physics was totally clear to Geoffrey Hinton. So this is an actual quote for him from the New York Times interviews, that Hopfield nets use an energy function. Boltzmann machines use ideas from statistical physics. So at that stage, neural networks did depend a lot on ideas on physics. Okay, so although not a physicist himself, he worked a lot on ideas of physics and applied physical principles to build architectures that are used in computer science. Okay, so the idea of Hopfield, again, if I go back, is to imagine learning as finding minima of an energy function. The idea that Hinton is using is that learning is sampling. So instead of locating the minima of an energy function using a deterministic dynamics, what we'll do is that we can imagine sampling the same energy function using the Boltzmann distribution, and then we can do annealing. So we can take the temperature going to 0, and the sampling will concentrate more and more on the minima of the energy function. So we know this. This is simulated annealing. This is used to solve optimization problem. And so in a sense, you can do sampling to achieve learning. In fact, you can do more because you can use this to learn distributions themselves. So imagine that you have a bunch of samples. So you have a huge samples of points. That sample of points is coming from some distribution. It represents a distribution. So the idea of Hinton is to represent that distribution as a Boltzmann distribution. And what you want to find is that you want to find the energy function that actually represents that distribution. So it's an inverse problem again. You want to represent the distribution of a random variable or the distribution of a sample of data points that you have, and then you're going to fit this to a Boltzmann distribution, and the inverse problem is to find the right energy function to represent that piece of data. So this is the in-physics problem. Now, imagine that you have Ising spin configurations, right? So I can simulate the Ising model. I can spit out some configurations. I can take the temperature going to 0, and I'm going to go more and more into the 2 ground states, the all spin up and the all spin down, and I can show you this as the 2 ground states of the Hamiltonian. And so you can imagine that then if I give you just configurations from my sampling of the Ising model, the inverse problem will be, what is the energy function that gave rise to that sample, right? But the samples don't need to be Ising configurations. They can be anything. They can be pictures of cats, right? So if you have a sample of data, that can be anything. If you have a sample of pictures of cats, you can try to represent this as a distribution, a Boltzmann distribution, and then your goal is to find the energy function associated with the pictures of cats. So you're finding the energy function, the cat energy function, okay? And this is what modern machine learning is doing. It's really representing distributions of data, of very complicated data as some kind of architecture, a Boltzmann machine, a Boltzmann energy function, or something else. And then we'll discuss that something else later. So here we have a different idea. So before we had learning as optimization, now we have learning as sampling. And this is really important. Okay, so the goal, of course, now is to find this energy function. You have a bunch of data. You want to actually fit now an energy function. How do you do this? There's an infinite number of ways you can fit an Hamiltonian actually to a bunch of data. It just depends on how you represent that Hamiltonian. Do you put two-body interactions? Do you put three-body interactions? Whatever. The idea of Hinton was to introduce the idea of hidden layers, so hidden units. So we're not going to represent the data using just x like before, p of x. What we'll do is that we'll build the Boltzmann distribution of p of x. X will be the visible layer. This is where the data will be. Then we're going to have another layer, the hidden layer, which will be part of the x, and so it will be part of the energy function. So we have visible units. These are like the bits of my images. The hidden units are not seen. They're just states that are behind, and then we have behind them, we have weights behind them. And in the model of Hinton, actually, there's no self-link between the units here, like in the Hopfield network. You only have weights between the hidden layer and the visible layer. There's also no weights between the hidden units. And this will make actually the learning more efficient. So it's a given architecture. It's not clear at this point why we should use this, but this is more efficient than the Hopfield network. So it looks like a Hopfield network. It's just a divided network with hidden units. The Hamiltonian that Hinton uses is this one. So you have correlation with the weights between the hidden and the visible layers. And then you have a kind of magnetic field for the associated with each units of the visible layer, and the same for the hidden layers. So these are like biases, right? So you have a bunch of B's, a bunch of A's, and then you have the weights. And the goal, of course, is to learn all of this. So how do you do this? You have to find the weights in order to maximize the likelihood of the distribution average over the data. Okay, so this is kind of the loss that you have to, instead of just using a loss where you're trying to minimize the output with the data you have, you want to maximize the likelihood that if you put the data point here, the distribution that you find gives you the maximum. So this is maximum likelihood. And this is the principle that you're going to use in order to find the correct weights, find the correct biases. Now, this is a difficult problem if I just state this as a maximization problem. But the good thing about this architecture is that you can do actually a gradient descent optimization method for solving the maximum. And then the gradient step will be easy. And so this is the reason for actually choosing this particular architecture, because the gradient of, forgot the parentheses here, the gradient of the likelihood is actually just the mean interaction with the hidden layer minus the mean interaction, but reverse this. So you have, sorry. So this is the mean interaction with the visible layer for the distribution that you're trying to find minus what actually the data tells you. So you're trying to reach what the mean interaction or the mean field would be for the distribution that you're trying to learn. And so when you reach the distribution of the data, this will be 0, and so there's no further gradient of the loss function, and so you've reached the maximum of the loss. Okay? So the two ideas here is hidden units and gradient descent. And the gradient descent for the learning, because learning is an optimization problem. But now you're not learning just on some deterministic energy function, but you're learning on average as a sampling problem. You're learning the Boltzmann distribution of the data. And that, in a sense, is what Hinton contributed in '83.
So could you say what the intuition is behind adding these hidden units? What are they buying us?
Yes. Yeah. So the idea is really something also very physical, is the fact that you're creating correlation by putting units on the side. Okay, so in the Hopfield network, everything is connected to everything, so everything is fully correlated, and then you kind of freeze the network with that kind of correlation. With Hinton, what you have is that you actually you don't have any correlation between the units, so that makes the model simpler, and what you do instead is that you trade off by putting correlation in some hidden units. And that really is the crucial idea and the idea behind the deep neural networks that we have these days.
But is it clear that this should help, like a priori, if I didn't do any experiment?
I don't think so. I mean, I'm not sure what's the sequence of thinking that Hinton, I haven't read the papers, also all the papers myself, but this particular architecture is attractive because the gradient step is very simple. See, this is the difficulty. If you want to do gradient descent for a certain loss, if the gradient is not explicit or if it cannot be computed efficiently, you're stuck. Okay, and this is why backpropagation for feed-forward networks is actually efficient. So this is why these networks are used nowadays. So I'll come back to this. Okay, so I would say the idea is an idea of efficiency and an idea rooted, well, first I mentioned this, so learning a distribution instead of an energy function, and then using an architecture that will make the learning simpler.
So, how do you compute the xi h alpha data? So, x is the hidden layer.
Yes.
X is the.
These are the bias in the hidden layer. You have access to this.
Yeah. So, I was just how do you compute xi h alpha of the data?
The data is given, right? So it's like you have your cat pictures. So I can calculate an expectation like this on the data. Each picture will have a certain configuration of xi. Yeah.
So what will be x alpha for?
Again?
H is the hidden.
Oh no, H, the data actually will be fed here. H is just a bunch of states that are not related to data. You're fixing this yourself. No. But you'll be changing the weights, connecting those weights, those units using the gradient descent step. Yes.
Maybe I'll ask the inverse question. So I guess the data I found simpler to understand. The 1 over P of X, are you just generating samples from the current
Distributions? Yes.
Okay.
So this one is given by the data. This
Yeah.
one you'll do by Monte Carlo.
Okay, got
Yes. Yes. So you'll be sampling. So this can be calculated efficiently. Analytically, you wouldn't be able to calculate this, but by Monte Carlo, you can just generate samples of your Boltzmann distribution and estimate that expectation. So this is coming from Monte Carlo, this is coming from data. So the gradient step, in fact, is a stochastic gradient step.
How do you compute this data? Because you have only X as data.
Yeah, so you have a bunch of images. So you're going to sum this for all the images that you have.
H is a hidden units, you don't know.
Yeah, no, you know H. It's hidden in the sense that it's not the stuff that's being fed through the data, but you do have the H's. The H's are given. You're going to play with the H's. Yes.
No, but I thought this correlation you have to compute from the data. This correlation next.
Yes. But in your architecture, you have the H's. So you have to compare, you have to do the scalar product with the H's in order to compare what's the correlation of the H's with the distribution that you're trying to learn, and what's the correlation with the H with the data that is given. H is given. You're playing with H.
If the number of purple and green balls were like the same,
Yes.
then you still have order n squared rates, right?
Yes.
And in the previous Hopfield case, we also have the same number.
Yes, but the dynamics is very different. For some reason, first, I mean, conceptually, we're learning something different, right? We have more flexibility in the way that we're learning a distribution and not just running a deterministic dynamic. So that might add to the capacity or efficiency. But also the architecture is different.
Why is this architecture more efficient for computing?
This I'm not so sure. They just realized that it was more efficient, but it's efficient in two ways. You can store, well, first you're not storing just patterns. You're learning a full distribution. So in a sense, you have more freedom in the representation that you're learning in that respect. But the efficiency is also in the learning. Once you've learned your weights, there's no more dynamics that you have to run in order to recognize a pattern, right? So after you've done all the learning with the stochastic gradient algorithm, what you have is a bunch of weights and a bunch of biases which actually represent a distribution. So you've learned a distribution, you've learned a random variable. At that point, it becomes like a generative model. You can actually draw a sample from this, and the samples would look like the data you have. So this is more like a generative model. Slightly different actually from the way that you're learning an input-output relationship. Here, you're really learning a distribution. But I'll show later on that it's more or less the same. You just have to make that conceptual step actually of learning a function is not so different from learning a distribution.
Just to clarify, this maximum likelihood that you're talking about, that's marginalized over the hidden.
Oh, yes, forgot to mention this. So this is the full model with the hidden. Of course, when you're going to do your Monte Carlo, you're going to draw just from X. So you marginalize. So you trace out the H out of it. So this might actually answer the question there is that the full model is with H and X, but what you generate at the end is really P of X. So you actually discard the hidden unit, but the correlation is built in the hidden unit. When you do the trace out, you actually get a very complicated distribution. And it's because of that trace out that you get a very complicated distribution. So physically, it makes sense, right? Imagine a big quantum dynamics over n particle. You look at one of them, at one atom, which is the trace out of the rest. The dynamics of the atom itself is very complicated. It comes from all the correlations and all the dynamics, the n-body dynamics that is being reduced to one unit. Okay, so this is more or less the idea. And we see again that this is very physical. I mean, if computer scientists or even physicists have any doubt that Hinton actually deserves a Nobel Prize, well, you just have to see this or actually just show them the Hinton and Hintonian to be satisfied. Okay, so this contribution of hidden unit, again, I mentioned this is really the main idea that we use nowadays. So the neural networks that we use like transformers or convolution neural nets or like the modern apps that we have are based on this notion of feed-forward deep neural networks, okay? Variations of them, but the idea is really to have hidden layer, and this is coming from the restricted Boltzmann machine. You have the input layer there, and then you have the output. So you're just going forward in time. It looks a bit like a Hopfield dynamics in the sense that the different units will be updated in the layers, not in time now, but spatially in the layers, using a sum, a weighted sum, and some transfer function. So, which can be the sign function, but people use other functions like what we call ReLU or the hyperbolic tangent function. The point is that the sigma has to be nonlinear. This is really important in the learning. And the way that you do the learning is that you minimize the output that the network gives you compared to the data that you want to match. Okay, so this is really a kind of classification task, and then you minimize the output error of your networks. And this is how you're going to fix now the different weights or the different biases to make sure that the output matches the data that you want to fit. Now, the reason why we use these type of networks is because you can do gradient descent also on this. So you can do a learning on the weights using gradient descent, and then the gradient can be calculated efficiently in one pass that we call backpropagation. And this is really the reason why we use these networks, is because the learning for these networks is efficient, even for huge deep neural networks. Deep, actually, the way we teach it is more than 2. If you have 3 layers, this is considered deep. But the type of deep networks that big companies like Google use nowadays is like thousands of layers with thousands of units per layer. So these are huge neural networks that can represent very complicated functions.
Hidden layer had connections in between itself, then you wouldn't use backpropagation?
Again?
If the hidden layer itself had connections between itself, like in the Hopfield network,
Yeah.
then you wouldn't use this backpropagation?
Precisely. So the reason why backpropagation or gradient descent is useful is because there's no connection between them. There's an efficient way of calculating the grade, right? The point again is that you want to change each of the weights individually. Now, what you can do is that you can do one pass forward and then another pass forward for 2 different images, and then you calculate the distance, and then you try to fiddle that little weight in order to minimize the distance. This will be totally non-efficient. Okay, and so people initially, when they devised the feed-forward network, actually had no way efficiently to find the correct weights that would achieve the minimized error. So they were doing just try and error in order to change the weights. You can do this by simulated annealing, but it's also not efficient. And so backpropagation came, and then people realized that, oh, in one pass, we can update all the weights in one go, and that's because of the precise architecture that you're using.
The question. So apart from this ease of use, like things like we can use things like backprop, is there any other reason why the time, like using time dynamics as a thing to minimize energy is now gone out of the picture?
Well, the thing is that you have to do the learning only once, right? Once a neural network has been learned or you found the correct weights to represent the function, then you can just sell that network as, it becomes just a function. You've learned a function, and so you can put an input and it will tell you what the output should be. So this is used, for instance, in image classification. You put images of cats and dogs at the entry, and then the output will be, this is a cat or this is a dog. Okay, so there's no more, once you've done the learning of the weights, there's no more dynamics to be done.
The weights were also learned before, right? Like once the weights are learned, that's it.
That's it. So it's not like a Hopfield network. Hopfield network, the weights are determined, but in order to recognize a pattern, you have to run it dynamically.
So
Here, of course, you have to do a forward pass, but that forward pass is very efficient. You don't have to do a dynamics, which will be like an exponentially converging dynamics to an energy minimum. Here, the time it takes to do a function call is only proportional to the number of layers that you have.
So it's like fixing the number of times you're calling the layer.
Yeah. But at the end, once you've learned, this is just a black box. You have an input, it gives you an output, and it gives you the right input. Yes? Yes.
On X, H, the layers, and now you have some deterministic.
Yes. I was going to say just that, actually. So here what I'm describing is a deterministic input-output relationship. But actually, now you can use this also to learn distribution. Because imagine, again, these cats and dogs pictures, and then you have, this is a cat, this is a dog. But actually, what you can do instead is you can put your images as input, and the output will be, this is a cat with probability this. This is a dog with probability this. So you're learning really a distribution inside for what is the distribution in the world of cats and dog pictures. And in fact, you can do this not only to, I put here the output layer as being one node, but it could be a whole output layer itself. And so you can output something also that will be actually another random variable related to it. So here you're learning a relationship, not like learning a distribution, but you can still use this to learn a distribution. I don't know if you...
Part of your data, and then you have a deterministic construction to
Yes.
complete sample of your...
Yes. The construction is totally deterministic, but the Hinton network is also completely deterministic, right? It's a deterministic representation of a deterministic energy function, but because it's used in the Boltzmann distribution, it's a representation of a distribution. Here what I'm saying is that the forward network, feed-forward network, learns a function, but you can also use it to learn distributions. Okay. It's another conceptual step. But people use this really to learn distribution. And so this has been actually the background for the breakthrough applications that came and then led to what we have like ChatGPT now and all these image or text recognition applications. So the first one was what's called MNIST in 2004. MNIST is a collection of written decimals, numbers, and then there was a challenge or a task actually to build a neural network to recognize these images. And so that was done with feed-forward neural network with the best classification, like the minimal classification error in 2004. And then from there, actually, that's where everything started in terms of revolution in using feed-forward networks and then leading to the technologies that we have now. So convolution networks, recurrent neural networks, the deep Q-learning networks that we use in AlphaGo, AlphaZero, and AlphaFold are also based on this idea of feed-forward networks. And the transformers are variations of these networks too, and then transformers is the basis of ChatGPT. Okay, so I want to finish with, so we have that technology, we realize the contributions, and of course, it's being applied now a lot in life, in the way that we write, in the way that we can do things in industry, but in physics also. So there's not a week in PRL where you don't have a paper on machine learning, and there's just going to be more because you have this tool on the table that you can use to do physics. And this is the first application of machine learning is machine learning used as a tool to do physics. So for instance, you can build neural networks that will classify phase transitions. So you give configurations of your system, and then the network can tell you whether you're in this phase or that phase. You can imagine also that at CERN, with all the tracks of particles that they have, they're not actually classifying particle tracks in any human way. They use computers for this, and nowadays they're using also neural networks to do this. And so this is a very efficient way of doing particle detection classification. In astronomy, the same problem. If you want to catalog galaxies in the skies, you can put humans to do this, but it's more efficient to have a machine that can actually spot different objects automatically and then classify those objects and then list the objects that look more interesting, and so we can focus on those. And this is done actually on a wide scale. And then you have other applications like using neural network for molecular dynamics simulation, fluid simulation, material design. And one big application that we've seen lately is Google and DeepMind using neural networks to learn the mapping of amino acids to functions of big complex molecule. And this is done by an engine that's called AlphaFold. And this is interesting because this is the prize in chemistry this year. So this year we have 2 prizes for machine learning, one for physics and then one also in chemistry. I would say actually this one is slightly more controversial to me than the physics prize, and then we can discuss this why later. It's not the subject of this talk, but for sure this is worthy of a Nobel Prize, but there's something in it that's a bit funny. So this is also driven by neural networks. And there's another way that you can see also machine learning as being related to physics is that there's lots of fundamental research now in physics that actually go in the direction of understanding what machine learning is. So the connection is like spin glasses. So there's lots of theory of neural networks now that use spin glasses techniques in order to show how many patterns you can store, what's the convergence properties, why are neural network actually learning at all. Lots of people are trying to study these big questions using ideas of statistical physics and particularly ideas of spin glasses. There's also different architectures that came out recently, like something called neural differential equations, which is really something physical and something fundamental. And the connection really is the learning dynamics. Learning is a dynamics, and dynamics is physics, so learning is physics. And it's something even more deep, if you want. You can use machine learning to discover physics. So at the most fundamental, we could give data to a computer, and the data could try to understand what are the physical laws that explain the data that we see, which is what we do as humans, right? But there are people thinking that we might reach a stage where computers themselves can discover physics. And I'll leave you with this idea. It's controversial in its sense. We think that, you know, machine learning might replace a lot of people, but not us, for sure. But, you know, you might have to actually think twice about that. Okay, and I'll finish with this slide. So the fact that we have all these neural networks is very clear to us, actually, that it's a revolution in the way that we imagine computing, but it's really something fundamental, and probably even more fundamental that we think it is. And I'd like to just draw this slide to your attention, is that when we do computing, really, we have the old model of computing. Computing is logical. It's based on logic. We have Boolean calculus. Computers represent zeros and ones, so it's obvious that they do Boolean calculus as a machine. And then this is also built in the way that when you do program, you're just encoding the rules. So programming languages are just expressions of logic. And you have rule-based system and procedural programming, and these are the current computers that we have. This is how we do computing now. But neural network is just changing this idea. You have something completely different now. It's not based on logic, it's based on neurons, so it's based on dynamics. So computation now is not logic, it's really a physical dynamics, and then you have this idea that learning is an optimization. So there are no explicit rules, it's non-procedural, yet we're learning something useful, and this is the kind of current applications that we have, and it's a fundamentally different models of computing that we're used to. And so at the moment, we have these tools actually sitting here and there, and of course, this is actually programmed on top of this, right? But you can imagine that we could build computers that are fundamentally neural networks and not just based on Boolean logic. And so these are the new AI tools that we have, and then we'll have more of them. So gradually, I think we might move towards that side. And one way to actually illustrate this is chess playing. So you might have heard about AlphaGo. AlphaGo was the engine devised by DeepMind to play Go, and it actually won over one of the master of Go in 2015. And then later on, they started playing chess too, but before, the computer chess engines were based on rules. They were based on expert system. You needed Russians on your team to actually program those computers. And the latest incarnation, probably the best incarnation of this was Deep Blue. Okay, which could beat actually Kasparov at some point, but Deep Blue was based on explicit coding of what chess is, openings, and then searching rules to find the best ways of playing chess. After AlphaGo, there's something that came that's called AlphaZero, and AlphaZero just throws, all of this out of the window. There's no explicit rules that you need to code. The neural network will learn those rules. It will learn to play chess. You can have two neural networks playing chess against each other to learn what chess is, and they learn this gradually, and they actually beat anything that you can program using expert systems. Okay, and so that's the new paradigm. You're not building or coding something explicitly, you let a machine learn what it should learn. And this is more efficient in certain ways, and it shows in the applications that we have of this, and for instance, for AlphaFold. So AlphaFold is a bit like this. There's no hard coding chemistry in AlphaFold. AlphaFold is just learning chemistry. Okay, so I'll stop on this. I'll give you references. If you're interested in learning machine learning or integrating this into your research as a physicist, there are many sources and material that you can use. I'm just putting some here. There's one very famous one that came just before COVID. I think everybody was reading this during COVID. It's a physics report, a high bias, low variance introduction to machine learning. This is very good, actually. It's a review of many different architectures and machine learning and different ways of imagining machine learning, like supervised machine learning, unsupervised machine learning. And what's good about this is that they have also Python code to help you practice this and learn this, so that's quite good. In terms of a list of applications of machine learning in physics, there's a review of Modern Physics 2019 on this. A good way to start slowly into neural networks is this small book, free book actually, by Michael Nielsen. Michael Nielsen is the author of this Bible on quantum computing, and then he just went into neural networks and then wrote this. I also like Melich. This is the book here. This one is more classical on Hopfield neural network, Boltzmann machines, and the dynamics, and so the convergence, the capacity, and the efficiency of all of this. And the Bible of deep learning is a book by Jan Goodfellow, Yosha Bienjo, and Haran Corville. This one is also free. It's got a website there, so you can use it. And if you're interested in the history and the controversy of neural networks and who invented what, then this book that I find really interesting, it's called An Oral History of Neural Networks. It's just a bunch of interviews with the big people actually doing neural networks in the 70s and 60s and 50s, including an interview with Geoffrey Hinton. So I'll finish here. Thank you for your attention.